Hello, this is Mr. Huber. In this lesson, we're going to learn about factoring special products. First, let's recall the two special products of binomials we looked at. First, if we have something like 2x plus 5 squared. So when we're squaring a binomial, like 2x plus 5, that's 2x plus 5, right, times 2x plus 5. That's going to be 4x squared. Our end term is going to be plus 25. Don't forget there's that middle term. We multiply 2x times 5 and get 10x, and then double it in the middle, and we're going to get 20x. So we have 2x plus 5 times itself. So we'd have 2x times 2x, which is 4x squared. Then we'd have 2x times 5 twice in the middle, the two like terms that would add together. So you multiply these together and then double it, remember, to get the middle term, and then 5 times 5 would give us the 25. That would be a perfect square trinomial. This next example, we have a plus and a minus, the same binomial, but they're different signs in there. So the middle terms will cancel, and we'd end up with 3x times 3x, which is 9x squared, and minus 64. Because we'd have a plus 24 and a minus 24 in the middle, it would add together and cancel out to 0. So those are our two special products. Factoring means we're going to take this product and find out what the factors were that multiplied together to get us that polynomial. Remember, factoring is something that would divide evenly into a quantity. Right? That's what factors are. So when you find the factors of 36, for instance, these are all numbers that we could divide into 36 evenly with no remainder. And these are all numbers that would multiply times some other number in this list and get us 36, including if it was 6 times itself. 6 times another number in the list would be 6. But we have 1 times 36 equals 36. 2 times 18. 3 times 12, and so on. These are all factors of 36. So we're going to find out what are the factors that would multiply to give us a polynomial instead of what are the factors that multiply to give us a number like 36. So to factor polynomials, we're going to look at special patterns here. And remember, factors are going to multiply together and get us that original polynomial when we're done. Just like the factors of 36 multiplied together and gave us the original number of 36 if we multiplied them together. So first, let's see the difference of two squares. So the difference of two squares. Difference means subtracting two squares. A squared minus b squared. And that would always result in a plus b times a minus b, right? Where the middle term would cancel out, as we saw when we multiplied those together earlier. So right here, 4x squared minus 9. 4x squared is 2x times 2x. And 9 is 3 times 3. So the factors of this would be 2x minus 3 and 2x plus 3. So the 2x and the 3 are two parts of the binomial. And when it's a difference of squares, we're going to have different signs on the binomials. 1 plus and 1 minus. So let's see what that looks like when we factor some difference of squares here. 25x squared minus 81. So we want to find out what would multiply together and give us 25x squared. Well, that would be 5x. What would multiply together and give us 81? Well, that would be 9. And the difference of squares means they're going to have a binomial where there's two different signs. So 5x plus 9 and 5x minus 9. And you can write the minus 9 first and the plus 9 as the second binomial. It doesn't matter. They just have to be 1 plus and 1 minus. So now we have 16n squared minus 49. So that would be 4n. And I'll write this one first as the minus 7 and then 4n plus 7. Okay? Because 4n times 4n would give us 16n squared, and negative 7 times 7 would give us minus 49. Or if we distributed and multiplied this all the way out, which we shouldn't need to do, we should recognize these special patterns. Right in the middle, we'd have 4n times 7, which is 28n. And we'd have minus 7 times 4, which is minus 28n. Right? Those cancel out. That's why we don't see anything with just an n in it here as a middle term. So that's a difference of squares. Figure out what times itself would give me the first term, what times itself would give me the second term. And then make sure we have different signs on our two binomials. The other special pattern is for perfect square trinomials. Perfect square trinomials would be ones where we have, for instance, x squared and 9, which we can find something that times itself gives me x and times itself gives me 9, x times x and 3 times 3. When I multiply them together and double it, I'll get the middle term. Right? So that's our two patterns here. Right? This is a times b and then doubled times 2. When you multiply something by times 2, you're doubling it. So we're going to take these two terms and multiply them together and double it to get our middle term. We're going to take x times 3, right, which is 3x, and double it would give us 6x. We want to recognize that so we can write the factor. So we want to look at, in these polynomials that are examples here, we're going to find out what multiplies together and gives me m, and what multiplies together and gives me 36. So that's going to be m and 6. And now, whether it's plus or minus is going to be determined by the middle sign. We want to double something and get negative 12, so we have to double a negative amount. So it's going to be m minus 6 squared. It would be m minus 6 times m minus 6. Right? If I multiplied this back out, right, our special pattern here, I'd have m times m, which is m squared. Negative 6 times negative 6 is 36. Multiplied these together, negative 6m doubled is the minus 12m. Right? In this next example, we have 9x squared would be 3x. 4 would be 2 times 2, and we want to add, because we're going to want a positive, 3x times 2 is 6x, doubled is positive 12x. So that sign is going to be the same as what's in our perfect square trinomial. If it's a minus for our middle term, it's a minus. If it's a plus for our middle term, it's a plus. Okay, we want to recognize these patterns. We've been multiplying these to get the product right here. Now we want to take this and find the factors. The factors are, if I multiplied this together, I would get back to my original quantity, my original, in this case, polynomial. All right. We're going to see some more examples as well, but before we do, before Mount Everest was discovered, what was the highest mountain in the world? A little bit of a tricky question because it was Mount Everest. Before it was discovered, it was still the tallest mountain in the world, so Mount Everest, even before it was discovered. All right. Now let's see some more factoring. Before we factor a polynomial, look for special patterns and things like that, the first thing we always want to do is find a greatest common factor. Okay, greatest common factor. We're going to see what that looks like. So when we see this polynomial, we want to look for it. Common means it has to be the greatest factor of all of the terms. It has to be common to every term in the polynomial. Here there's 3 terms. If there was 4 terms, 2 terms, 18 terms, to be the greatest common factor, it has to be a factor of all of the terms. And here you could look and see 8, 20, and 100. We want to find what's a factor of 8, 20, and 100. You might be thinking 2. And 2 is a factor, but it's not the greatest common factor. 4 is also a factor of all 3 of those terms, 8, 20, and negative 100. So I can factor out a 4, and then I would have left 2x, because the factors that would give me 8 would be 4 times 2. The factors that would give me 20 would be 4 times 5x, and the factors that would give me 100 would be 4 times 25. All right, so 4 times 2, what's the greatest common factor? Factors of 8, factors of 20, and factors of 100, and 4 is the biggest number that's a factor of all 3 of those terms. So this would be how we could factor something like this. Right? Look at here, let's find a greatest common factor of 3y squared minus 36y plus 108. So if we're going to find a greatest common factor here, it's 3. And then we're going to have y squared. 3 times 1 would give me 3. I don't have to write the 1 in front of the y squared. If you do, it's not wrong. You don't need to. Minus 12y. And now we want to see what are the factors of 108. And some of these numbers, as they're bigger, finding the factors can be more challenging and figuring out what's a common factor. Okay, so we can do that here. It's going to be 36 times 3. Right? And now we've taken out a greatest common factor. And we're going to see next, what we're going to want to do is see, is there a way to factor this any further? Right? Is there something else I can do to factor this? So we're going to see that next. We'll do it here as a first example. So yes, I can. Right? This would be y minus 6 and y minus 6, or y minus 6 squared. Right? This is a perfect square trinomial. So we want to look for that. We took out a common factor, and now what we have left over here can still be factored further. Right? And I want to make sure I write my 3 down because it's still a factor. If I want to multiply together all of this and get back to where I started right here, I can't forget the 3. If I just multiply y minus 6 times y minus 6, I'll get back here in blue, but I won't get back to my original amount. And keep in mind as well, right, we could write this as 3 and then y minus 6 squared. All right, so now let's see some more examples. We're going to factor completely. So it means everything we can possibly do to factor these, we want to. All right, let's look at number 5. And first thing we should look for, is there a common factor? If there is, we want to factor that out first. So here there is, there's a 2. Then I'd have y squared minus 10y plus 25. And like in that last example, we can see that what we have in the parentheses there is still a perfect square, so I can factor that further. That's y minus 5 squared. Right? I'd have y times y to give me y squared. I'd have 5 times 5, and it's a minus because if I multiply these together and double it, I'd get negative 10y. All right, now in number 6. In number 6, there's no common factor to take out, right? There's not always going to be a common factor because we see that that's an option. Doesn't mean it always works, but you want to try that first. Always start with a greatest common factor. In this case, there's no greatest common factor, so I want to look for what are my special patterns. And it is. It's a difference of two perfect squares. These are both perfect squares, 7 times 7 and 12 times 12, and then all of my variables that goes with those coefficients as well. So I'd have 7m plus 12n and 7m minus 12n. Don't forget the n on those second terms. That's fine, right? Because n times n to give me n squared. Hasn't changed. Different as squares, 1 plus and 1 minus. These are both the same binomial, just that different sign there in the middle. All right, on number 7, okay, I do have a greatest common factor here. So my greatest common factor of these is 5. So I factor out of 5, then I have 4n squared minus 9. And now I want to see is what's in parentheses can be factored further, and it can. So since it can, I want to do that. And I'm going to make the 5 stays a 5, and I have 2n plus 3 and 2n minus 3. Right? That's a difference of squares on our special patterns there. Number 8, we're going to look for no common factor, but it is one of our special patterns. This is a perfect square trinomial. That's going to give me x plus 6 squared. 6 times 6 is 36. X times 6 is 6x. Doubled would give me the 12x there in the middle. So again, look for a greatest common factor. Also look for those special patterns to factor completely. 2 more examples. Again, be trying these on your own. Let's see if you're starting to understand how you can factor these. First, we want to look for a greatest common factor in number 9. There is a greatest common factor, right? It's not 9. Okay, you might be thinking, oh, I can take a 9 out of both these. Yeah, but 9 is not a factor of 75. So it's got to be a common factor to all of the terms. So in this case, what that would be a 3. So I can factor out a 3, and then I'll get 9x squared minus 30xy plus 25y squared. Okay. Now I want to look at my trinomial here and see if this can be factored further. And this is a perfect square. 3 times 3 will give me 9, so 3x. 5 times 5, and I have the y, so 5y. And if I multiply those together and get 15 and double it, I'll get 30. So I want to pay attention to my signs I have there. We got a lot going on in this problem because we've got double variables, we've got common factors. So I'm going to have 3x minus 5y squared. I have a minus there because I'm subtracting the middle. If I multiply these together and double it, I want to get negative 15xy doubled to give me negative 30xy. And in my last example, number 10, so I don't have a common factor. 181 don't have any common factors. So I'm going to just factor this as a difference of squares. 10 plus 9r and 10 minus 9r. And you could write it as 10 minus 9r and then the 10 plus 9r. It doesn't matter which one of these is the plus and which one is the minus as long as one of each. Okay? And keep in mind, you could also multiply this back together. If you want to find out if something are factors of the original amount, multiply them and see if they get what you started. Right? We just went to 36, the number, right? You want to say, oh, are 3 and 12 factors of 36? Yes, because 3 times 12 is 36. So if I want to see are these factors of my polynomial, then I multiply this together. I should end up with 100 minus 81r squared. All right, so factoring, look for greatest common factors, and we want to be recognizing those special patterns with our perfect square trinomials. Right? That's what this is, a perfect square trinomial where the first and last terms are perfect squares, and when you multiply them together and double it, you get the middle term. When there's no middle term, we just have a difference. Right? If this was plus, it wouldn't work, but a difference of two squares, then I have different signs on my two binomials, which are the perfect squares of 100, which is 10 times 10, and 81r, which is 9r and 9r.